graduated from Punjab University, Patiala in 2003. She completed her PhD in Computer Science and Engineering at NIT Jalandhar in 2015. Dr. Rani began her teaching career as a lecturer at Guru Nanak Dev Engineering College, Ludhiana from 2003 to 2005. She joined NIT Jalandhar in 2007 and has since made significant contributions to the institution. With over 100 publications in reputed journals and conferences, Dr. Rani is a recognized authority in her field. She has also served as co-investigator on numerous research projects, particularly in the area of image processing. Her primary research interests include image processing, computer vision, and machine or deep learning. Dr. Rani is also committed to excellence in teaching, which was acknowledged when she received the Best Teacher Award at NIT Jalandhar in 2023. In addition to her academic and research achievements, Dr. Rani is actively involved in mentoring students and guiding them in their research projects. She has been instrumental in organizing various workshops, seminars, and conferences to foster a collaborative research environment. Her dedication to advancing the field of computer science and engineering is evident in her ongoing efforts to integrate cutting edge technologies into the curriculum and research initiatives at NIT Jalandhar. Please join me in welcoming Dr. Rajneesh Rani, who will surely inspire and enlighten us with her knowledge and insights in today's session. Ma'am, over to you.
Thank you. Thank you, Ishika, for nice introduction. So first, I would like to share my presentation. Yes, is screen visible?
Yes, ma'am.
Yes.
So today I will discuss the concept of transfer learning and pre-trained models. Before starting the exact topic, transfer learning and pre-trained models, I would just like to introduce the concept of AI and machine learning. And I think in this course, you have already discussed about these concepts. So first of all, I would like to know from the audience that how much concepts are clear of convolution neural network and recurrent neural network. Because if these concepts are clear to you, only then I can better explain the concept of transfer learning. Yes, concept of CNN, RNN, AI, and deep learnings are clear to everyone. Okay.
Yes, ma'am. They have completed all these neural network in the previous sessions.
Okay. So I will just skip this portion by giving a brief introduction. That is what is AI. AI is just, we can say, to mimic the natural intelligence. So AI is a subset of computer science where machines can appear to be intelligent by running programs. So we can say here AI means just a replicate of natural intelligence. In, if we say applications of AI is used everywhere, for in every field. For example, we can say assisting doctors, then automating grading system, vehicle, autonomous vehicles, business for smoothing overall process, then travel industry for predicting pricing patterns, social media for serving personalized experience. These are the general applications of AI. And if we say, come to the concept of machine learning, machine learning is a type of artificial intelligence. And here we make the machine to learn with the help of some algorithms. And from these learned models, the machine makes the prediction for the unknown data. And when machine, in case of image processing, the concept of deep learning is there, which just you can say advanced version of machine learning. If we say in the above figure, there is an image of a car, and the machine wants to recognize what type of object it is, whether it is a car or not a car. So in case of machine learning, the programmer has to retrieve some features from this image using some heuristic techniques, for example statistical features, structural features, and after that extracting these features, some learning algorithm is applied, machine learning algorithm is applied. For example, you can say svm, knn, or adaboost to classify this particular image. But in case of deep learning, the feature extraction phase is also done by your system rather than by the individual human being that is developing some algorithm to extract the features. All these things are done by the neural network. So if we say just the hierarchy, then we can say AI, then the concept of machine learning, and then the concept of deep learning. That means deep learning is a subset of machine learning, which is a subset of AI. So AI, again, in case of AI, basic three concepts are there. One is the just your simple neural network, feed forward neural network, then CNN, then RNN. I think most of the concepts are clear to you. That is what is ANN, feed forward neural network, simple neural network. Neurons are there, input layer, hidden layers, and output layers are there. So the basic concept for every neural network is a back propagation. So then that means how this learning takes place in case of neural network, that is only with the help of back propagation. That is, training is done and the final output is compared with the actual output, labeled data is given, and whatever the error, that is back propagated, and according to the error, weights of the neural networks are updated. And uh, just we can say these weights are updated till our error is or loss of the network is minimum. So next concept is convolutional neural network. This is just a simple feed forward neural network. Next is convolutional neural network. Here the concept of just we can say convolution operation is there, as image is a two-dimensional data. So rather than applying inputs as directly to the neural network, convolution operation is done. So in case of convolutional neural network, a number of convolution layers and max pool layers is there. Next type of neural network is recurrent neural network. In case of recurrent neural network, we can say it works for the sequential data. For example, we can say NLP, textual data. Here, rather than just we can say giving the input at a single time step, at multiple timestamps the input is given. So recurrent neural networks are used for the just we can say time series or NLP applications. Now again, some concepts of neural networks in case of supervised learning, that is whenever there is labeled data is there. Then unsupervised learning, when we have no labeled data, unlabeled data is there, but depending upon some catching, just we can say equivalence of the images or similar patterns in the images, we cluster them into the different classes. Next concept is reinforcement learning. Reinforcement learning, here the machine learns by taking a reward. So deep learning plays an important role in all these type of learning: supervised, unsupervised, and reinforcement learning. But in case of deep learning, there are two major challenges. What are these two major challenges? Yes, as you have learned a lot of things about CNN earlier in the earlier sessions, what are the major challenges in the deep learning? Anyone?
Parameter tuning.
Yeah. As we have discussed in this slide, that is in case of back propagation, whatever the error is there, according to that error, weights are updated, right? Now, in case of deep learning, we have a number of parameters. in case of deep learning. Why a number of these parameters? Because a number of layers are there in between. And at each layer, a number of neurons are there. And for these neurons, a number of weights are there. So these weights are updated after each training example is given to the network. So when these weights are updated, then that means uh, training here means just to train these parameters, these weights, to get the exact values of these weights. So this is the major challenge in case of deep learning, as a number of layers are there, a number of neurons are there. So that means a number of parameters are there. So training a network means to find the optimal values of these parameters using the training data. So how much training data is required? Depending upon the number of parameters. If number of parameters are too much, then that means we need a lot of training data. Why? Now see, in this, just you can say, why we need so much data. This is clear from the simple problem, that is problem of linear algebra. See, if we have just two parameters in a equation, then we can say we need at least two or three equations to know the exact value of these parameters. So similarly, if we have unknown parameters, that is in millions, then we need data in millions to find these unknown parameters. If we have a very few data, then we cannot get the exact values of these training parameters. We can just get the only the approximate values. And if we approximate value, then we cannot have exact output of the we cannot have exact output for the unseen data. So the major problem for deep learning is just requires large amount of labeled data. But for some problems, we cannot have such type of labeled data. Now next is just we can say high computational requirements. High computational requirements, if we want to know so many parameters, we need to have, or you can say we need to train our network for hundreds of hours. So that means we need high computational requirements. So to solve this problem, just the solution is transfer learning. So what is the concept of transfer learning? Just we can say again, it is similar to the natural behavior. As in our real life, we just can see that is whatever we learn in our real life, we can apply that knowledge to solve some other similar type of problem. Same concept is there. That is, we can train a model on some data set, and same model can be used to solve a similar type of problem, but not exactly same. So transfer learning is an advanced field of deep learning in which a solution or algorithm is made to solve one problem, and it can be used to solve another problem of similar type. For example, model generated for recognition of trucks can be used somewhat for recognition of cars also. So in this diagram, you can say source labels are there, and here source model is there. And this model is trained on some source data. For example, you can say any publicly available data set, you can train your model on any publicly available data set. Here ImageNet has been shown. Now, whatever the model has just gained the training, after that training, same model can be applied to solve another problem. Then that means same, this model has learned some knowledge, and that knowledge is transferred to solve some other type of problem. Now in this slide, you can see the difference between the traditional learning and transfer learning. You can see here three different tasks are there. One is just to recognize these circles or ellipses. One is just to recognize these triangles and these square boxes or diamond shapes. So to solve each type of problem, different learning algorithm is there. Then that means in case of traditional learning, to solve each type of problem, we have to make a different algorithm, different model. But in case of transfer learning, just we can see our model is trained on ellipses, circles, and triangles, and that knowledge is transferred to solve this thing. What is this thing? To recognize these, just you can say rectangles or diamonds. So then that means your model has been trained on different type of data, and that model is used to solve different type of tasks. Then that means just we have transferred the knowledge that is acquired from anything else, and that knowledge is used to solve some different type of problem. So transfer learning makes the learning fast by making the use of the already learned weights to train the pre-trained network. Pre-trained networks, which are trained on large data set, are used to provide the solution for the data having small data set. That means for particular some problem, we cannot have sufficient data. So we can build a model and then train that model with the data which is available, large data set. And now that model can be used to solve other problem which is having the small data set. So this transfer learning solves the problem using two approaches. One is the pre-trained network as a feature extractor, and next one is the fine tuning the pre-trained network. Then that means the concept of transfer learning can be used in two ways. Either as such use the pre-trained networks or fine tune the pre-trained networks. Two approaches are there. Either use the pre-trained network as such or fine tune the pre-trained network. So we can see here what is the concept of this, that is fine tuning and without fine tuning. Now see here, this is an example of a neural network, simple feed forward neural network. Here we can see there are two type of layers. One is the freeze layer and one is the trainable layers. Frozen layers are the layers of the pre-trained model that are kept unchanged during the fine-tuning process. Frozen layers retain the knowledge learned from the original task and are used to extract general features from the input data. Then that means here, whatever the layers of the original network, freezed layers weights are never changed. When you apply, uh, you can say, when this network is once trained on a data set, and after that, this some weights are there for each layer. Weights are having some values, and now these weights are not changed for the frozen layer when you solve your different type of problem using this network. Frozen layer means all the weights are freezed. These weights are now never changed. Modifiable layers means these are the layers of the model that are adjusted or retrained during the fine tuning. So you can see here some trainable layers. Trainable layers means now you can change the weights of these layers, trainable layers, according to the data of your new problem. Then that means modifiable layers learn task specific features from the new data set. By focusing on these layers, the model can adapt to the specific requirements of the new task. That means now these layers at the end, these are the trainable layers. These weights are changed according to your data. So what is the meaning of this? That is, whenever a model is trained on the existing publicly available, or you can say large data set, and that model is once trained, and then after training, the weights will have, the trainable parameters will have some values, And now that network is used to solve a type of problem which is having a smaller data set. Now, whether to use the existing network as such, or you want to modify that network according to your new data set, this depends upon you. You can use some layers of the existing network as the freeze layers and some other layers as the modifiable layers. Now, which layers to freeze and which layers to require modification, that depends. Which layers we need to freeze and which layers to train. So the more you want to inherit features from a pre-trained model, the more you have to freeze layers. That means if your pre-trained model is similar to your new problem, then that means you can make many of the layers as non-modifiable, that is frozen layers. But if your data set is totally different and you are having sufficient data, then you can make many layers as the modifiable layers. So you have to take the different situations. Consider all the situation where the size and data set of the target task vary from the base network. The target data set is small and similar to the base network data set. So first is that is your new problem data set is small, and this new problem is similar to the problem on which your network is trained. At that time, what will you do? You will make many of the layers as the frozen layers and only one or two layers at the last as the modifiable layers. Why at the last? Because last layers of the network learn high level features and initial layers learn low level features. And the last layer of the network is just your having the number of neurons depending upon your classification problem, whether 10 classes, whether 2 classes, whether 3 classes. So your problem can be different according to the number of classes. So the last layer you have to change almost every time. For example, one problem can be there just to classify the digits 1 to 0 to 9. So it is a 10 class problem. You want to, you have a can have binary classification problem, whether a particular person is having suffering from cancer or not. So it is a binary classification problem. So at the last layer, whether you need 10 neurons or 2 neurons, last layer you have to change every time. But before the last layer, if your target data set is small and similar to the base network, you cannot modify any of these layers. Next is the target data set is large and similar to the base training data set. If your target data set, again, it is large, but it is similar to the base training network, then you can make at the last 3 or 4 layers as the modifiable layers. If the target data is small and different from the base network dataset, in this case, again, you can make the last some layers as the modifiable layers and the initial layers as the frozen layers. If the target dataset is large and different from the base network dataset, then you can say you can make every layer as the trainable layer. Then that means you can now do fine tuning of your data set by changing all the parameters according to the data set of your new problem. I think it is clear. Yes, any doubt in these 4 points?
Yes, fine.
So next is state of the art. I think concept of transfer learning is clear. What is transfer learning? Now the concept of pre-trained models. See, pre-trained models means in Kera's library or researchers have developed various models, different architectures of the just you can say deep neural networks having different type of features, and these networks are trained on the ImageNet dataset. So now these network architectures are easily available, publicly available, and trained weights are also available publicly. And these pre-trained networks now can be used to solve any different type of problem. So these are just, you can say, some pre-trained networks for the object classification, and below some pre-trained models for the object detection. VGG16, Inception, ResNet, MobileNet, Exception. So these architectures we will discuss in today's lecture. And for object detection, RCNN, faster RCNN, single shot detector, these architectures are for the object detection. But in today's lecture, we will discuss only the pre-trained models for the object classification. So whenever we say pre-trained networks available, these networks come into two parts. One is the architecture part and one is the weights part. Architecture is how many layers are there, and then just we case at each layer how many neurons are there, which layer is connected to which layer, all these things. And at each layer what type of kernels are there, and what is the size of the kernel. And in weights file means whatever the weights, the parameters have got the values after training on the ImageNet dataset. So the very first model was the AlexNet model. So AlexNet model was introduced in 2012, and it is a breakthrough in deep learning, winning the ImageNet large scale visual recognition challenge. This model was having 8 layers, 5 convolution layers followed by 3 fully connected layers with ReLU activation function, max pool, and dropout to prevent overfitting. So we can see this is the very basic model, and it is having 5 convolution layers and 3 fully connected layers. And in each layer, ReLU activation function was there. Just 1 second. Yes, sorry, just for the interruption. Yes, in this AlexNet architecture, 8 layers are there, 5 convolution layers and 3 fully connected layers. Now you can see this is a simple sequential neural network. You can see simple sequential neural network. Each layer is having different kernel size and different just number of filters, and mostly just the activation function that is used in each layer was the ReLU activation function. And the limitation of this AlexNet was the high computational cost, because this model is having 60 million parameters, making it large and challenging to deploy on devices with limited memory. So it is the in today's day, it is just a outdated architecture. Next, in 2014, next architecture was the VGG16. So just it is developed, introduced by Visual Geometry Group, and it is again able to classify 1,000 images of 1,000 different categories with 92.7% accuracy. Now you can see why it is called 16, because it consists of 16 layers. Why it is called 16? Because it consists of 16 layers, in which 13 layers are the convolution layers and 3 layers are the fully connected layers. The model is also known for its simplicity and uniform structure, using only 3 into 3 convolutional filters and 2 into 2 max pool layers. So you can see here, different blocks are there. After first two convolution layer, we have one pooling layer. Again, after convolution layer, we have pooling layer. Again, after 3 convolution layers, we are having pooling layer. Again, after 3 convolution layer, we have pooling layer. So what is the purpose of pooling layer? Pooling layer is just to reduce the dimension and number of parameters. So we can say the primary strength of VGG16 is in its depth, which allows it to learn complex features from the image. That means here a number of layers are there. So we can see at the initial layers will extract the low level features of the image, and at the last layers extract the high level features of the image. So you can see the architecture of VGG16 in detail. We can see here first layer 64 filters of size 3 into 3 into 3. Second convolution layer 64 filters of size 3 into 3 into 64 with a stride of 1 and activation function as the ReLU activation function. You can see here in first block we have 64 filters, then in the next block we have 128 filters, in the next block we have 256 filter, and the last two blocks we have 512 filters. So limitations, again, it is very slow to train because a number of parameters are there. Size of the VGG16 trained image consists of 528 MB, leading to high memory use and longer training times. So we can see 138 million parameters are there. So many number of parameters are there, then that means we need a lot of data to train this model. Next concept is of inception V3. What is inception V3? Now see, the concept of inception V3 came in 2014. Just we can see, as in the previous architectures, we have just seen the sequential architecture. Sequential means one layer after the other layer and other layer after the previous layer. But in case of inception module, we have parallel layers. Functional architecture is there. What is the concept of inception module? Just we can see, in case we have a particular object in an image but of different size. For example, an image can have an object car having small size. In another image, same car is there but of different size because the image has been captured from the closer. So how to capture that the object is of the same, that image is of the same object? Then that means we have to extract the features in such a way that we can recognize the object even having different size into the same category. For that, we have to apply convolution operation using different filter size and at the same layer. So you can see in this inception module, you can see here 1 into 1 convolution layer, 3 into 3 convolution layer, 5 into 5 convolution layer. Then that means inception modules use 1 into 1, 3 into 3, and 5 into 5 convolutions simultaneously, followed by max pool to capture various levels of detail in the input data. Inception uses 1 into 1 convolutions to reduce the dimensionality of the input before applying more computationally expensive layers. So 1 into 1, 3 into 3, 5 into 5. These convolutions are applied just to have capture the features of the same object having different size. But before these 3 into 3 convolution, 5 into 5 convolution, we apply this 1 into 1 and 1 into 1 convolution. Why? Just to reduce the dimensionality of the input. Just you can see here. Yes, I think you have the idea how to calculate the number of parameters. If you have the idea of calculating the number of parameters, then this concept is will be more clear to you. How to calculate the number of parameters. Yes, do you have the idea? See, for instance, we need to perform 5 into 5 convolution without using 1 into 1 convolution. You can see this is an image size of 14 into 14 into 480. Let us suppose on this image, we apply directly 5 into 5 convolution rather than applying 1 into 1 convolution. And the number of filters are 48. Then how many operations will be there? How many computational operations will be there? You can see 14 into 14 into 480. And when we apply 5 into 5, the number of operations involved is 14 into 14 into 480 multiplied by 5 into 5 into 48. And that is equal to 112.9 million. But if we apply 1 into 1 convolution before 5 into 5 convolution. If we apply 1 into 1 convolution before 5 into 5 convolution, then we can see the number of operations reduced to only 5.3 million. Here, number of operations are 112.9 million, and here number of operations are 5.3 million. How? You can see here. Here number of filters are 16. In 1 into 1 convolution, number of filters are 16. So the number of operations for 1 into 1 convolution is 14 into 14 into 16 multiplied by this 1 into 1 into 480 multiplied by 1 into 1 into 480. So that is 1.5 million. And after that, this 5 into 5 convolution, number of operations are 14 into 14 into 48. That is this 14 into 14 into 48 multiplied by 5 into 5 into 16. That is 3.8 million. So after addition, we will get 5.3 million. So now it is clear. If we apply direct 5 into 5 convolution, we have the size 112.9 m. But if before applying this 5 into 5 convolution, we apply first 1 into 1 convolution, then the number of parameter reduced to only this. So this concept is used in the inception module. So you can see here, as we can see here, this is only 1 into 1 convolution direct, so no need to apply 1 into 1 convolution before. But here 3 into 3 convolution, so rather than applying direct 3 into 3 convolution, we apply first 1 into 1 convolution. Again, rather than applying 5 into 5 convolution direct, we apply first 1 into 1 convolution. And here from the previous max pool, after max pool, we apply 1 into 1 convolution just to keep the number of parameters same. So now after this, all the values are concatenated. So this is the basic version, inception version 1. This module is the inception version 1. After a modifications came into this inception version 1. So this is just inception ResNet A block, ResNet B block. We will discuss ResNet in the next architecture. But here you can see simple inception module. This is just, you can say, the previous layer 1 into 1, 1 into 1, 1 into 1. And this 1 into 1 convolution is applied before 3 into 3. Now you can see here, rather than applying 5 into 5 convolution, we are having we have divided this 5 into 5 convolution into two convolutions, that is 3 into 3 and 3 into 3. And here we have block B 1 into 7 and 7 into 1. And here 3 into 3 convolution is divided into 1 into 3 and 3 into 1, just to reduce the number of parameters. And some reduction block is there. Reduction blocks are used to just reduce the number of parameters. Now, using these different blocks, GoogleNet architecture is there. So in GoogleNet architecture, basically this architecture is also called inception network. These are the inception modules, inception blocks. And now these inception modules are used in a number sequentially, and inception network is formed. So the inception model's architecture is complex, making it difficult to understand, implement, and modify compared to simpler models. This is the limitation of this. Despite optimizations, inception models still require significant computational resources, especially in their deeper versions. So the basic concept of VGG16 and inception 3 is clear? Yes? Am I audible? Am I audible?
Yes, madam, you are right.
Yes, any doubt in VGG16 and inception? So now we move towards the next model, that is ResNet architecture. Should I move forward?
Yes, madam.
Okay. So the previous models, the VGG16 and Inception 3, these suffer from a major problem. What is that problem? Vanishing gradient problem. I think all of you have learned this term, that is vanishing gradient problem. Can anybody explain what is that problem, vanishing gradient problem? What is vanishing gradient problem? See, vanishing gradient is, see this architecture. This one. Now see, I have said that the network training of the network is done by comparing the output of the model with the actual output, and whatever the difference, that is back propagated. Now this difference is back propagated with the help of derivatives. So whatever the difference is there, the difference, actual difference, is at the last layer. Now this difference is back propagated to the previous layers and using the derivatives. So whatever the difference, that is multiplied by the, just you can say, derivatives. So whatever the difference is there, that is again back propagated and multiplied by the derivatives of this layer, derivatives of the weights of this layer. So then that means when this back propagation is done, ultimately the initial layers, the value of these derivatives will become nearly zero. Then that means now these weights of initial layers will not be updated. Your gradient vanishes. Gradient vanishes means derivative when multiplied with a lower value, 0.0000 something, so then that means it will become approximately to zero. So then that means your gradient vanishes. Your gradient vanishes and weights are not updated. Training is not done properly. So to solve this problem, the concept of skip connection was there. Skip connections were introduced by the at the Microsoft Research in 2015, and this new architecture was named as residual network. So what is the concept behind this? That after some layers, the inputs are added to the output. You can see here This is the skip connection. X is also added to the output of this layer. So then that means now when the back propagation is done, these weights are not, or these gradients will not become equal to zero because some addition is also there. So the residual blocks help to solve the problem of vanishing or exploding gradient. ResNet models are computationally intensive and require substantial resources for training and deployment. They can overfit on small data sets due to their depth and large number of parameters. The deep architecture leads to longer inference time and high memory uses. So if you say the ResNet architecture, different type of architectures are there. You have, I think you have listened these terms: ResNet 18, ResNet 34, ResNet 50, ResNet 101. What is the meaning of this? This is the meaning of this means how many number of layers are there. So you can see these are the different architectures in inputs, and just you can see uh, in 18 layers these are just convolution 2 modules are there with having only 2 convolution layers. In 34 layers we have 3 convolution layers in the first block, and in 50 layers we are having 3, but having, just you can see, 1 into 1, 3 into 3, 64. So these 3 layers are having will be repeated 3 times, then that means 9 layers, then 101, then 152. So different type of resonant architectures are there, having different number of layers and number of filters and number of filter sizes. So here at the right hand side I have just shown one architecture diagram, that is just you can say resonant 18. Max pool layer is there, then 3 into 3 convolution layer with 64 filters, 3 into 3 convolution layer, 64 filters. Here I have strides by stride 2. Dotted means by stride 2, by stride 2, with stride 2. So just this is, you can say, in this architecture, after some time, or you can say after some layers, we have the skip connections. Skip connection means whatever the output here, that is added at this layer. Whatever the input you are giving to this layer, that is added to this layer. Then the input to this layer is added to this layer to solve the problem of vanishing gradient. So next is the Inception ResNet V2 module. This is just, you can say, the combination of previous two models, that is Inception module as well as the ResNet module. Inception ResNet version 2 was introduced in 2016, and it combined the strength of Inception modules and residual connections from ResNet, creating a powerful and efficient architecture. It is one of the deeper neural networks incorporating both, that is inception and residual layers, leading to improved accuracy on large-scale image recognition tasks. The residual connections help mitigate the vanishing gradient problem, allowing for training of very deep networks without significant performance degradation. Limitations. What are the limitations? Again, high computational cost, complex architecture, memory uses, and inference time. So this is just an architecture of Inception ResNet. Here's some reduction module. You can see reduction modules, Inception ResNet A, ResNet B, that we have discussed in the previous slides. Next concept is mobile net. The concept of mobile net is just the concept of depth-wise separable convolution. And this concept will be clear to you only if you know how actually the convolution operation A performs. MobileNet was introduced by researchers from Google in 2017, and it is designed for mobile and edge devices with reduced computational complexity using depth-wise separable convolutions. Now, what are depth-wise separable convolution? You can see here from the figure. In the standard convolution, when you apply convolution operation, all the convolution operations are done at all the channels and then addition is done. I think it is clear how convolution operation is performed on a multi-channel image. Yes, I will just show. I want to like one presentation to you. Slides are visible. I want to just show how convolution operation performs in multi-channel. See, let us suppose this is the image having three different channels. Now see, this is the image having three different channels. When convolution operation is performed on this image, how, let us suppose these are the kernel values. So at each time, the kernel is multiplied with each channel. So channel 1 is multiplied by with this, channel 2 is multiplied by with this, channel 3 is multiplied by with this, and then these values are added and the final output is there. Yes, this is clear.
Yes, madam.
Now you, from this slide, I think it is clear to you, that is whenever you apply standard convolution operation, all these three channels just come to with one, and when number of filters are applied, you will get similarly an image having different number of channels. But now see, in this case, a number of calculations are there. So a number of calculations are there, and then that means these uh, networks cannot be used for the small devices, for example edge devices or mobile devices, because a number of computations are required. To solve this problem, the concept of depth-wise separable convolution was introduced. Now, what was this concept? Rather than applying convolution operation at all the channels, operation is performed just at different channels, depth-wise. Different channels, that is, if a number 32 channels are there, then that means at each layer, each channel, different type of convolution, or you can say different convolution operation is performed. So you can say in depth-wise convolution, each filter applies to only one channel of the input image, processing each channel separately. This reduces the computational load compared to applying the filter across all the channels simultaneously. So in standard convolution operation, all the operations are done in one step. In depth-wise separable convolution, convolution is performed in two steps. First is the depth-wise. Depth-wise means at each channel, and then point-wise. In point-wise convolution means we apply one into one filter to combine the outputs from the depth-wise convolution across all channels. This step merges the information from different channels, allowing the model to learn more complex features. So you can see here first, you can see this figure one, and then according to this next channel, according to this next channel, and you get this output. Then on this output, one into one simple convolution is applied, and that convolution adds all this information. So now this operation is divided into two parts, but here number of computations are reduced very much. So by taking the concept of this depth-wise convolution, basic two architectures have been introduced. One is the mobile net and other is the exception network. So in case of mobile net, this you can see here depth-wise separable convolution, depth-wise separable convolution. It is again a layered architecture. Just we can say, as we have discussed, VGG16 or ResNet, it is not having the concept of inception net, but it is a layered architecture rather than functional architecture. But the concept is having only depth-wise separable convolution rather than having simple traditional convolution. So this model sacrifices some precision compared to larger models, may not scale well for complex tasks or large data set. Inference speed is slower on larger inputs, and optimization tuning parameters can be challenging. So next model using the same concept of depth-wise separable convolution was introduced in 2017. It is a combination of your inception architecture as well as depth-wise separable convolution. Then that means inception plus, just you can say the concept of depth-wise separable convolution is called exception. That is extreme inception. The model separates spatial convolution from the channel-wise complete, reducing computational cost while maintaining high performance. Exception achieves better accuracy and efficiency than inception V3 on various tasks, demonstrating the power of depth-wise convolution, separable convolution. Limitation: high computational demand, overfitting risk, inference speed, complexity in deployment. So this is just you can see now here you can see the concept of separable convolution is there, as well the concept of ResNet module is there, as well as the concept of inception module is there. Basically this architecture has been divided into three parts: entry flow, middle flow, and exit flow. In entry flow, just we extract the low level features, just simple convolution layers can be there, and in the middle flow separable convolution layers are there and having a number of units. You can see here this same module is multiplied by repeated 8 times, and the exit flow to extract the high level features. So these were the pre-trained models, existing pre-trained models for the classification problem. AlexNet, VGG16, Inception V3. This is a summary for all the models that we have discussed in this lecture. So I think all the base idea of all the architectures is clear. Should we move to practical session?
Yes, ma'am.
Okay. So for practical session, just I will show one slide, and then I will explain one code that is on the Kaggle site. So just I am explaining first this one. So whenever you want to use any pre-trained model, basically there are two things. First, you have to load the pre-trained model with its weights. So you can see base model is equal to MobileNet V2. Here I have used MobileNet V2 model as the pre-trained model, and weights is equal to ImageNet. That means initial weights of the network are the weights that were just weights trained from the ImageNet dataset. Include top is equal to false. Include top is equal to false means the last layer has not been included, because last layer we have to add according to our own problem. Then input shape, that is whatever the input shape model is getting, that you have to specify here. For example, mobile net is taking 96 3 3 means 3 RGB image. Now add custom top layers, then that means this is base model, is mobile net v2. Initial layers of the mobile net v2 has been taken for your final model, and at last whatever the output of that model, you are flattening that output. Then output layer is equal to dense 10. Now dense 10 means here I have added a fully connected layer to solve a problem of digit classification, that is MNIST data set. So activation function I have taken softmax, and then we have created the model. And you can see here, freeze the base model layers. For layer in base model layers, layer dot trainable is equal to false. What is the meaning of this statement? That is, all the base model layers are just kept as frozen layers rather than modifiable layers. And whenever we will train the model, only these two layers will be trained. So this is just, you can say, the base of the implementation of your pre-trained model on any new data set. I think this basic concept how a pre-trained model to be used in the Python code using Kera's library is clear to you. Now I will just move to the application. Now you can see I am just this one. Control C. I have just shared a link in the chat box. You can go through this Kaggle notebook. Take 5 minutes. You can click on this link. Take 5 minutes and just try to explore this code. Then we will discuss this code in this session. Yes, I think link is available to everyone.
The link is not working.
Not working? But here it is working. I have clicked from here. Yes.
Not working. Message is coming. You can't find this page.
But मेरे तो यहाँ पे. Okay, then I will just share the code here in the, just typing in the chat box. Just wait. Yes, Dr. Abhishek, I have shared one file with you.
Yes, ma'am. I have shared in the Canvas. Everyone, please log into the Canvas and check the file over there. Click on the link, and you will be redirected to that page
So
and download that file.
I can, that file is basically using dog breed classification for dog breed classification problem. And first I will explain this, uh, just you can say, on the CIFAR dataset, Kaggle dataset having VGG16. But if this link is not working, you can try that file that I have shared already with the Dr. Abhishek. Now you can see here in this particular code, CIFAR 10 using VGG16, these are just the libraries from the TensorFlow that you have to import. And here you can see one thing from tensorflow.keras.application.vgg16, import VGG16. See this one, this line from tensorflow.keras.applications.vgg16, import VGG16. So then that means using this, you are just importing your pre-trained model. You are importing pre-trained models. Both the things you are importing, that is model architecture as well as model weights. Now you can see here VGG16 underscore model is equal to VGG16 weights is equal to ImageNet, include top is equal to false, classes is equal to 10, input shape is equal to 32 comma 32 comma 3. Then that means this model has been imported into your notebook, and the weights are of the ImageNet data set. So you can see when this particular cell will be run, then that means you will see this statement downloading data from this. Then all the weights, pre-trained model weights, you can see five approximately how many parameters are preloaded. Now now using this VGG16 pre-trained model, you are building your own model. Model is equal to sequential. Now for layer in VGG16 model dot layers, model dot add layer. Then that means whatever the layers in the VGG16 models, you are adding all those layers in your own model, sequential model. So you can see here, after adding all the layers of the VGG16, you are adding some of the layers of your own. So these are just, you can say, at the end, that is one is the flatten layer. Then after flatten layer, just some layers are fully connected layers. Three fully connected layers are there having number of filters 512, 256, and at the last layer, because 10 uh, classes problem is there, so at the last layer we have only 10 neurons and some dropout layers are there. So you can see the final architecture of your model. You can see here model dot summary, final architecture of your model. You can see the initial layers of the model are all those layers which are of VGG16, and this after VGG16, these are some of the layers, that is flatten layer, hidden layer, dropout layer. These are the layers that you have added at your own. So total parameters are so much, trainable parameters are so much. All the parameters are trainable. So now just you can see this one. Now I am solving CIFAR 10 data set. What is this CIFAR 10 data set? This is just a data set having 10 different type of objects. So this data set is having 60,000 images. 50,000 images are the training data set, and in 10,000 images are in the testing data set. So this is just to as you have done earlier in convolutional neural networks in the earlier sessions, this is just how the training is done. That is, you are just dividing your classes into the two categorical, that is one hot encoding is used, then this normalization is done, then this is just your training data is split into training and validation, and this is just stochastic gradient descent has been taken as your optimizer, then model has been compiled and checkpoint has been introduced, and some augmentation of the data is done, and you can see this statement model.fit generator. When you apply this thing, then that means training is done. Just model.load weights are loaded. You can see this one. So here training is done, and after that you can get the training accuracy, validation accuracy, and the test accuracy. So this is the way how to solve your problem, any problem, using a pre-trained model. Now whatever the file I have given to Dr. Abhishek and shared with you, that is on the dog breed classification. So in the dog breed classification, first you have to download the data set, that is the dog breed data set, that you can download from this site. Again, I will share the link in the chat box. So you can download this data set from here, and you can just run that file. I will show I have run that file in Google Colab and just showing that slide. Just wait. So you can see this one. Here you can see I have implemented the model, that is just I have implemented in this, I think VGG16. VGG16 has been implemented, but using dog for the dog breed classification problem. So you can go through this file and just try yourself. I am here. If any problem is there, just you can understand this code. And if any problem is there, you can just discuss with me. Yes, Dr. Abhishek?
Yes, ma'am.
I am here first because I think I have explained everything. First, participants should try this code on their own systems.
Okay, ma'am.
I am here for some time. If any problem is there to any participant, he or she can discuss with me.
Okay, ma'am. Okay.
Otherwise, if no doubt is there, I can leave the session. If any doubt will be there to anyone, then he or she can mail me.
If yes, ma'am, they can do that also. If they have a question, you can ask question right now, ma'am.
I am just typing my mail ID.
Okay, ma'am.
This topic is somewhat complex, but this topic will be clear only if they know the basic concepts of convolutional neural networks, how to calculate the number of parameters, how convolution operation is actually done. So basics are very much required to understand better these concepts, different, because each architecture is more complex and having different type of just you can say concept. For example, in inception network we have functional concept, and in ResNet we have the concept of skip connections. In MobileNet and exception we have the concept of depth-wise separable convolution. If the basics are clear of the convolution and how parameters are calculated, only then the concept of these pre-trained models will be more clear. Yes, any doubt to anyone? Okay. Dr. Abhishek,
Yes,
should I
ma'am.
leave?
Yes, ma'am, you can leave. If they are having some issue, then they can mail directly to you.
Okay. Thank you.
Okay, 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 ma'am. Uh,
On behalf
yes, yes, you can start.
On behalf of
It,
Faculty Development Program on Deep Learning Applications 2024 Organizing Committee, I thank the respected FTP speaker Dr. Rajneesh Rani for their valuable talk and hands-on session. With their permission, I am concluding this session. Thank you all. Next session will start at 6.
so we will start at 6. If you want to stay in the session, you can stay. Otherwise, we are closing this session right now.
Okay. Thank you,
Thank you
Dr.
very much,
Abhishek.
ma'am. Thank you very
Okay.
much, ma'am.
Thanks a lot.
Ishika, you are in the session. Ishika.